Your Daily Epsilon of Math is a calendar published by the American Mathematical Society. Every day it has a new maths problem. The aim is not just to solve the problem, but to think more about the mathematics involved. You can purchase the calendar either directly from the American Mathematical Society website or from Amazon. Today's problem is to find a polynomial p of y and a number x such that the following 5 constraints are true. The polynomial, when evaluated at 0, gives the number 104,729. The polynomial p has got integer coefficients. We're looking for a number x, which is itself an integer. This integer x satisfies p of x equals to x, and x must lie strictly between 0 and 104,729, the same number as here. We can also ask, is the answer unique? Now the calendar only asks us to find the number x. It doesn't actually ask us to find the polynomial p of y, but we do that as well. And we can also ask, is there anything special about this number here? Why did the people that made the calendar choose this particular number here? And would this problem still work with different numbers here? Let's recall quickly what a polynomial is. Start with some examples. A constant polynomial, p of y equals to some number. That means no matter what I choose for y equals to 0, y equals to 1, y equals to 23 million, y equals to the square root of pi, whatever value I choose for y, p of y just returns the number 23. So when we graph it, we just get a horizontal line at 23. A quadratic, again, is a special type of a polynomial, and it contains a term with a y squared in there, possibly a term with y there, although I don't have one here, and a constant term here, in this case -1. And again, a polynomial is just a rule. You give it a number and it will return a number by applying this rule here. In this case, the rule is y squared minus 1. So if y equals to 0, I substitute in y equals to 0. 0 squared is 0 minus 1, I get -1. Hence I've got this point down here. When x is 0, when my input is 0, it's a bit confusing here because they used p of y. And you normally talk about p of x when graphing something with y up here. But when the input along the horizontal axis, when the input is 0, when y equals to 0, the output, p of 0, is going to be -1. Hence we get this point here. When y is equal to 1, then 1 squared is 1, 1 minus 1 is 0. Therefore, when the input is 1, the output is 0. So we get this point here. Similarly, when the input is -1, -1 squared is 1, 1 minus 1 is 0. So the output will be 0. If the input is 2, then 2 squared minus 1 is 4 minus 1 or 3. So when I move across here 2 units, I need to move up 3 units. 2 squared minus 1 is 3, and plot that point here. So in general, a polynomial is something that we can graph like this. Given the input value, we can work out its output value. We can do this for all real numbers and end up with a graph. We can't get an arbitrary graph though with a polynomial. We can't get a sine wave, for example. We can't get an exponential. We can get a lot of functions though. And in fact, interestingly, we can come arbitrarily close to approximating any function we like on a finite interval. But a polynomial is restricted to have the following form. Basically, the rule can only involve a constant term and terms that contain just the variable to a positive integer, like y to the 100 or y to the 99 or y squared, for example. And the rule simply says, given a value for y, I'm going to take that value, raise it to some positive integer power, multiply it by the coefficient out the front, Remember that number. Do the same here. Given the number y, raise it to this power here, multiply it by the coefficient in front. Do that for each of the terms, then add them all up together. If n is 0, then we just have a constant polynomial, such as here. Otherwise, if n is 3, I'd have y to the power of 3, y to the power of 2, y and a constant. Some of these coefficients can, of course, be 0. We don't have to have all terms here. Here I'm missing the y term. Without loss of generality, we can assume the leading term here is non-zero, because otherwise I can just remove this term completely and change this to be n. We don't actually need to know the following to solve today's maths problem, but it does add a deeper perspective to what's going on. It's also basic knowledge whenever you talk about polynomial equations. Given a polynomial here on the left-hand side, I can try to find the value of y such that this is equal to any given value I like. For example, I might want to solve when the polynomial y squared plus y is equal to the number 6. The first thing to note is that I can always rewrite this as some polynomial equals to 0. Because a polynomial can contain a constant term, any number I have on the right-hand side, I can simply subtract off and bring it over to the left-hand side, and it just becomes part of my polynomial here. So without loss of generality, when we're interested in solving polynomial equations, we just have to be able to solve p of y equals to 0. When we understand this, we understand this as well. Graphically, we can visualize this as follows. On the left-hand side, I've got a function, y squared plus y, and I've drawn that here in red. Here's my function, y squared plus y. Y is the input, shown along the horizontal axis, and along the vertical axis, you plot what you get, what output you get for that corresponding input. So when y is equal to 1, then the output will be 1 squared plus 1 or 2. When the input is 1, the output's 2. When the input is 2, 2 squared plus 2 is 6. The output is 6 here. So to solve this equation, we can plot the left-hand side to get this red curve. We can plot the right-hand side. The right-hand side in this case is just a constant. And when you plot that constant, it looks like this. And solving this equals to this simply means finding the points of intersection. When does the red curve intersect the blue curve? And we see visually there are two solutions, one at -3, one at 2. We can verify that these are indeed the solutions to the equation by substituting them in. We already substituted 2 in to get 2 squared plus 2 equals to 6. If we substitute in -3, we get -3 squared is 9, minus 3 is 6. So these are indeed two solutions. You might ask, are there any other solutions? Well, graphically it doesn't look like there are, because as y gets bigger, this is going to get bigger. And as y gets smaller in the negative direction, this is also going to get larger. So it looks like there are only two solutions. We can actually study this mathematically. And interestingly, mathematically, we can prove that an nth degree polynomial, the degree of a polynomial, you look for the y to the largest power, and that largest power is the degree. So in this case, this is a degree 2 polynomial, also known as a quadratic. There's a beautiful theorem that says an nth degree polynomial has exactly n roots. A root is a solution to p of y equals to 0. And when we're solving y squared plus y equals to 6, because we can bring 6 over to the left-hand side, then this rule here applies to this case as well. So this tells us that because my polynomial has degree 2, there should be exactly two solutions, and here they are. Now, technically, you might say, well, x squared equals -1 has got no solutions, so that's why mathematicians, when applying this result, are working over what's known as the complex field. And so the two solutions there are going to be plus and minus the square root of -1, which is an imaginary number. And you might also say, well, x squared equals to 0 only has one solution, x equals to 0. But then mathematicians say, well, x squared equals to 0. If you were to perturb that 0 ever so slightly, you end up with two solutions. And so what's actually happened is that x squared equals to 0 actually has got two solutions on top of each other. And so that's known as the multiplicity, and that's how mathematicians get around the fact that for some very special cases, it looks like you have fewer than n solutions, but in fact they're stacked up on top. We don't need to understand any of these deeper results here, but they're good to know about, and hopefully will pique your curiosity for you to do some more reading. Tangentially, the way you can try to solve a polynomial equation by hand is by trying to factorize it here, and you can also go in the other direction. Given a factorization, you can expand it out to get the original polynomial here. Again, we don't actually need to know any of this to solve today's problem. Taking this broader perspective, though, makes today's problem look more intriguing, because if we remove the fact that we have integer requirements in the problem, then if p of y is a degree n polynomial, then p of x equals to x has got n solutions, possibly complex valued. And here we're looking for just a unique solution. So we want to try to understand why, on the one hand, this theory over here is telling us there should be lots of solutions, yet over here, we're going to find that there's only a unique number x that solves this. Of course, the key is that over here, we require x to be an integer, whereas over here, we're talking about the number of complex solutions. And in terms of solving this, we can indeed visualize it like we did before. We've got our polynomial p of y here, which we can graph it as a polynomial. And we want to solve p of x equals to x. Well, the trick for solving that, and it works for any function, not just polynomials, to find out when a function f of x is equal to x, in this case p of x equals to x, then what we do is we graph the function in blue. Then in red, we draw a 45-degree line corresponding to y equals to x, the graph of y equals to x. And where these two graphs intersect are the solutions to when the function evaluated at a point equals itself. Indeed, that's what y equals x does. Any value of x gives us the corresponding value of y. While we can and we will solve this problem purely algebraically, this graphical form makes the problem look more interesting because it's not clear why there should just be a single solution. It looks like there should be lots of solutions here. Given a problem, if you can't immediately see a solution, then you can start doing some trial and error experimentation. It might not give you the solution, but it often helps you to better understand the problem, and that will then lead to ideas for coming up with a rigorous solution. So for a trial and error solution in this case, we can simply try guessing a polynomial here. And we can do this by starting with very simple polynomials. The simplest polynomial would be a degree 0 polynomial or just a constant. And the next simplest would be a degree 1 polynomial, or in other words, p of y is equal to some number times y plus some other number. And we're going to look at both these cases here. It turns out that we can solve this using a degree 1 polynomial. But nevertheless, after we've found one solution, we'll then see if there are any other polynomials or any other values of x that can solve this in the general case. Start with a degree 0 polynomial. So we're trying to find a polynomial that is just a constant and for which we can satisfy these 5 things here. It may not be possible, but we'll try. So p of y has to be equal to some number because we've said it's a degree 0 polynomial. This might mean we can't find a solution, but trial and error, start with the simplest possible. Because p of 0 has to equal to 104,729, that means that requirement 1, together with our simplifying assumption that p of y is a degree 0 polynomial, that means that p of y has to equal this number here. It has got integer coefficients. Now we move on to finding a value of x that satisfies this. If this is my polynomial and I want to find an x such that p of x equals to x, then a moment's thought shows that there's only one solution, and that's x equals to 104,729. That it is a solution is easy to see. If my input, if y equals 104,729, if this is my input here, then my output is the same number. So indeed p of x equals to x if x is equal to this number here. To see that it's the only solution, try some other value of x. If x is equal to 0, p of x is equal to this number here. Well, that's not equal to 0, so that's not a solution. X equals to 1, my input's 1, my output is this number here, they're not equal. So again, a moment's thought will show us that the only solution to p of x equals to x for this particular polynomial is x equals to 104,729. And x is an integer, and p of x equals to x, but it fails this requirement here that says that x has to be strictly less than 104,729. So there is no solution if in addition to these 5 requirements, we have a 6th requirement that p of y is a degree 0 polynomial. In terms of trial and error, we now move on to the next simplest type of polynomial, a degree 1 polynomial. Can we find a degree 1 polynomial that also satisfies these 5 requirements? We can indeed solve this with a degree 1 polynomial, but that then leaves the question of whether there are other answers as well. Nevertheless, let's assume that p of y, in addition to satisfying our 5 requirements here, is also a degree 1 polynomial, which means that p of y is equal to some integer number here, integer because we're told that p has integer coefficients, so p of y equals some integer times y plus some other integer here. But a moment's thought shows that because we require p of 0 to be 104,729, this number here has to be 104,729. Indeed, if the input is 0 when y equals to 0, we've got something times 0 gives us 0. So the output, when the input is 0, the output is this number here. And because this number has to be 104,729, we therefore have to have 104,729 here. Okay, so by the simplifying assumption that p of y is a degree 1 polynomial, we're trying to solve this with p of y equals to some integer times y plus 104,729. We now have to see if we can find a solution in x that satisfies these requirements here. So p of x equals to x. That simply means I take this and replace y with x. So my integer times x plus 104,729, that's the left-hand side p of x, is equal to x. I'm trying to solve this. If this is confusing, then just substitute in particular values. For example, if my polynomial were p of y equals y plus 104,729, then when I try to find p of x equals to x, I get x plus 104,729 equals to x, in the special case that my coefficient here is 1. In this particular case, by moving x to this side, we end up with the equation 104,729 equals to 0. There is no solution. So let's try to better understand what this equation is telling us. Let's assume that my polynomial is p of y equals to 2 times y plus 104,729. So that means to solve this equation here, I've got 2 times x plus 104,729 equals to x. Over here, if my coefficient is 2, then 2x plus 104,729 equals to x. To solve this, I subtract x from both sides, so I get x plus 104,729 equals to 0. Subtracting off 104,729 from both sides shows me in this case x equals to negative 104,729. And so I have got a single integer solution, but it lies outside the required range of x strictly between 0 and 104,729. So the choice of 1 or 2 in here doesn't work. Can I find a number that does work? Well, trial and error, especially when we're dealing with numbers this large, is going to be quite tedious. Let's be a little bit smarter. Let's replace this squiggle with a coefficient alpha that can be anything. This just stands for some number that we're going to try to work out. So if p of y equals to alpha times y plus 104729, which is exactly the same thing as just saying a dashed line standing for some integer here, we just now represent the integer with alpha. If we want to solve this equation here, then we're solving alpha times x plus 104729 equals to x. Now we get to the algebraic stage here. Just as we did over here to solve these things here, we subtracted off x to bring it to this side here, and we move this number here to the other side by subtracting it. We do exactly the same here. So if you're uncomfortable, first do this with alpha equals to 1, then do it with alpha equals to 2, then do it with alpha equals to 3, and then when you're comfortable, you can just treat alpha as some box here, which is some number that we haven't specified, but we just treat as a number. So alpha x plus 104729 equals to x. I can subtract x from both sides. Alpha x minus x plus 104729 equals to 0. I can then factorize this term here. X is a common factor. This is alpha times x. This is negative 1 times x. So I've got alpha minus 1 in brackets times x plus this number equals to 0. And then I've done two things here. I have moved this to the other side where it would become negative 104729. And then for convenience, I've multiplied both sides by negative 1. So this now becomes positive here. And if I multiply alpha minus 1 by negative 1, it flips it around to be 1 minus alpha. Indeed, negative 1 times alpha is negative alpha, and negative 1 times negative 1 is 1. So after all this, if I have a degree 1 polynomial that satisfies the first 4 requirements, then I find that I have to solve this equation here to find my x. And this alpha here is just some integer that we're trying to find. It determines what my polynomial p of y is, and this x is another integer that we're trying to find. So if alpha is an integer, because p has got integer coefficients, and alpha is a coefficient of my polynomial, so it is an integer. If alpha is an integer, then 1 minus alpha is an integer. So I've got an integer times an integer equals to 104729. Just before I turn the page, have a think about how we're going to try to solve this and what it means, keeping in mind that this is an integer and this is an integer due to our requirements here. Recall that if we're trying to solve all of this under the additional assumption that p of y is not an arbitrary polynomial, but it's of the form of p of y equals to alpha times y plus 104729, then we end up with these requirements, requirements 1 to 4, are equivalent to solving this equation here, where both 1 minus alpha is an integer and x is an integer. And if we're trying to find two integers which when multiplied give me this integer here, well, that's factorization. We've now gone from polynomials, which belongs to complex analysis, we've now gone to number theory, which deals with prime factorizations, among other things. If I want to factor this number here, it's a bit larger than the numbers I'm used to, so there's no shame in asking Google, and we discover something nice. And not surprising, given that this calendar was put out to make people more interested in mathematics, we discover that 104729 is the 10,000th prime number. The fact that it's the 10,000th prime number is just a side note, something interesting. But the fact that it is a prime number is very important for this problem here, because it relates to the uniqueness question. If I had the number 10 here, then I could have a number of solutions here, because I can factor 10 as 1 times 10, or as 2 times 5, or as 5 times 2, or 10 times 1, or even negative numbers, -5 times -2 would give me 10. But because this is a prime number, we know that there's essentially only a unique factorization. Well, technically there's a unique factorization if I limit myself to positive integers. Because this is prime, the only solution in positive integers would be 1 times 104,729 in terms of a factorization. Here I've got two terms that are different. So in some sense I've got two positive solutions. This might be 1 and this might be 104,729. Or this term might be 104,729 and this one might be 1. But when I allow negative numbers, I now get 4 possible solutions. So x could be 1 or -1 or 104,729 or -104,729. To summarize, if I have got this equation here and I'm told that this first term is an integer and the second term is an integer, then there are 4 possible solutions in x. X might be 1 or -1 or 104,729 or -104,729, corresponding to the fact that 104,729 is a prime number, so it has only got 2 factors if we ignore the sign, 1 and itself. Requirement number 5 says that x has to lie between 0 and 104,729 exclusive. We exclude the endpoints here. And so out of these 4 possible solutions, we actually only have one solution that satisfies this 5th requirement here. And now you understand why the 5th requirement has chosen this number here, because we have to exclude the case when the other factor is a 1 and x is the number itself. So if p of y is a degree 1 polynomial, then the only possibility is that alpha equals -104,728 and x equals to 1. That's the only way we can satisfy all these requirements. Indeed, we've already argued that x has to equal to 1, so if x is 1, then 1 minus alpha has to equal to 104,729. 1 minus alpha equals to 104,729, and solving this is quite easy. We get alpha equals -104,728. So, subject to the additional assumption that p of y is a degree 1 polynomial, there's a unique solution. P of y has to be this polynomial here, and x has to equal 1. We first studied this problem when p of y was a degree 0 polynomial, and we found that there was no solution. There's no degree 0 polynomial that can be made to satisfy all 5 requirements here. Then we studied the case when p of y was a degree 1 polynomial, and we found there was precisely one degree 1 polynomial which satisfied the requirements here, and there was precisely one x which, for that particular polynomial, satisfied the requirements here. And so this is the unique solution to this problem, subject to p of y being either a degree 0 or a degree 1 polynomial. We also showed that 104,729 is special. For this problem, it's special because it's prime. If it were not prime, we could find multiple solutions to x and multiple polynomials here. We haven't solved this problem in its full generality though, because maybe there are other polynomials of higher degrees for which this is also true, and maybe for a higher degree polynomial p of y, there are more solutions other than just x equals to 1. Because we are dealing with integer solutions, we can't really use graphical methods to find the answer as we did at the start. It's not surprising that algebra lends itself to the solution here. And in fact, we can just basically extend what we've done before. Before, we restricted the form of p of y. We said p of y was a constant, couldn't find a solution. Then we said p of y was some number times y plus some other number. We found a solution. Now I want to let p of y be an arbitrary polynomial, but which satisfies the first 2 requirements. And how can I do that? Well, a little bit of thought shows that the first requirement means that I can rewrite P of y as P of y is equal to some polynomial times y plus this number here. Now, if you haven't seen this trick, it might take a few minutes for it to sink in. Remember that when we studied a degree 1 polynomial, I just had a number here. So all I've really done is replaced my number here with a polynomial. Although I won't do it here, to help you better understand this, you might like to take the example if h of y is equal to y minus 1, then you can replace this with y minus 1 in brackets, and you can do the multiplication here to get y squared minus y plus this, and you see you indeed get a polynomial coming out here. So if h of y is a polynomial, then this whole thing will be a polynomial. And moreover, when I evaluate it at 0, p at 0 equals to h at 0, and that could be any number I like depending on what h is. But p of 0 is equal to some number times 0 plus 104,729. And so therefore p of 0 is equal to 104,729. Conversely, any polynomial that satisfies p of 0 equals to this number here can be written in this form. And to see that, just write down an arbitrary polynomial, and you can leave the constant term there, and for the other terms, you can factor y out from it. And so here I've just factored the y out. So h of y just encodes all the higher order coefficients, and I still have my constant term here. I will elaborate on that at the very end of the video. For now, just assume that the first requirement means that p of y can be written in this form here, where h of y is an arbitrary polynomial, and then the second requirement that p has integer coefficients simply means that my h of y has got integer coefficients here. For the fourth requirement, we want to find a number x such that when we input x to our polynomial, we get x, the same number x coming out here. So solving p of x equals to x, well, algebraically, I just replace y with x. So when x goes in here, p of x is equal to h of x times x plus this number, h of x times x plus this number, and p of x equals to x, we want this to be equal to x, finding a particular number x. Now, just as we did in our special case before, we solve this in 2 easy steps. We bring x to this side here, and we bring this number to the other side here. And technically, I then multiply by -1 to simplify it. So any solution to this is also a solution to this, and conversely, any solution to this is a solution to this. These two are equivalent. The key point here is that x is an integer and all my coefficients are also integers. So in particular, at this point here, I have that x is an integer and h has got integer coefficients. What that really means is that if I put an integer into my polynomial, then because the only operations I can do are raise x to some power, multiply it by some coefficient, which is an integer coefficient, and add all the things together, that means h of x must be an integer. Whenever x is an integer, because my polynomial has integer coefficients, h of an integer is also an integer. And in particular, 1 minus h of x must be an integer. So in other words, any solution to this problem here with 5 requirements has to be that x is an integer and 1 minus hx is an integer. So we're back to where we were before. We're looking for integer factorizations of 104,729. And because this is a prime number, we know that there are only 4 possible solutions. X is 1 or -1 or 104,729 or -104,729. And because x lies between 0 and 104,729 exclusively, we know that x has to equal to 1, and that then means that 1 minus h of x is equal to 104,729, which we'll examine on the next page. So to solve this, we know that P of y has to be of the special form P of y equals to h of y times y plus 104,729. And from that, we deduced that x has to satisfy this equation here, where both this term and this term are integers. And given that x lies between these two numbers here, we conclude that x has to equal to 1. So in terms of x, which is all the calendar problem asked, the answer is unique. X has to equal to 1. In terms of the polynomial, though, there are actually many polynomials that give us that meet these requirements here. Indeed, the only requirement we have is that when x is equal to 1, so I substitute x equals to 1 in here, I get 1 times 1 minus h of 1 equals to 104,729. So 1 minus h of 1 is equal to 104,729. My polynomial h, which sits in front of the y term, so to speak, in P of y, that polynomial, it can be anything I like, provided when I evaluate it at 1, I get this number here. And there's an infinitely many number of such polynomials that satisfy this constraint here. So P of y is not unique. It takes a particular form. I can write down an arbitrary P of y that satisfies this. Indeed, P of y is equal to h of y times y plus 104,729, where h of y satisfies this condition here. Any solution of this is of this form here, so to speak. But it doesn't matter what polynomial I have for P of y, if it satisfies all of this, x equals to 1 is the unique answer. We now come to the appendix, where I promise to elaborate on why I claim that my P of y has to take this particular form here. And first I'll explain why by way of example, and then on the next page I'll give a somewhat complicated looking rigorous answer. But this should be good enough for most people. Because P of 0 has to equal 104,729, we know that P of y has to be something times y to some power plus blah 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 plus, and the constant term here, this constant has to be this number here. Because indeed, when we substitute 0 in, when y equals to 0, all these terms here out the front disappear, and I'm just left with my constant term. So in the problem, P of y has to be equal to something times y to the power of some high power plus something to another coefficient times y, etc., plus my constant term here. And the key point to get to here is that we just leave the constant term on its own, and every other term contains either y or y squared or y cubed or y to some power, and I can just factor y out of that. So in this simple example, if I have 3y squared minus 4y, every term contains at least a y, often y to some higher power. I just remove one y from each term. So 3y squared divided by y gives me 3y, and 4y divided by y gives me 4. So therefore 3y squared minus 4y can be written as y times 3y minus 4. And in general, any polynomial with this as its constant term, any other term, I can remove 1 degree from the y, so to speak, and therefore write it as some polynomial h of y times y plus that. If we want to do things completely rigorously, then to say that P of y is a polynomial, formally that means I can write P of y as a certain sum, and rather than just using dot dot dot, we use this summation notation. So I have got the sum as I goes from 0 to n, the degree of my polynomial, assuming the leading coefficient is non-zero, of my coefficient alpha I times y to the power of I. This is how we formally write what a polynomial is. Of course, that's the same as saying alpha 0 plus alpha 1 times y plus dot 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 plus alpha n minus 1 y to the n minus 1 plus alpha n y to the n. It's just a nicer way of writing the same thing. We know that P of 0 equals to 104,729. So when I substitute 0 into this, I get the sum of I equals 0 to n of alpha I times 0 to the power of I. And I know that 0 to the power of anything non-zero will give me 0, except for my the case when I equals to 0, because there I just have alpha 0 here. So therefore that's going to be equal to alpha 0. And so therefore P of 0 equals to 104,729 means that alpha 0 equals 104,729. So therefore P of y is equal to this expression here, together with the additional constraint that alpha 0 equals to 104,729. Now the next step is that I can expand this summation into the I equals to 0 term, so it's equal to 104,729 plus the sum of I equals to 1 to n of alpha I yi. Starting a new page, recall that P of y must be of the form 104,729 plus the sum of I equals 1 to n of alpha I, the coefficient, y to the power of I. And recall from earlier that what we want to do is factor out a y, so that motivates us to write this as 104,729 plus the sum of I equals to 1 to n of alpha I times the y that I want to factor out, and y times y of I minus 1, so y to the power of 1 times y of I minus 1 gives me y to the I, so that's correct, which is equal to 104,729 plus, now I can bring the factor out the front of the sum, and we want to call this h of y, and all that remains to show is that h of y, this term here, is an arbitrary polynomial. And to do that, we have to express it in the form of an arbitrary polynomial. That is, we want to show that h of y is of the form the sum of j equals 0 to some number, I'll call it big N, of some coefficient times y to the j, like that. We are not quite there because here the sum goes from 0 to some number, whereas here the sum goes from 1 to some number. And here we've got y to the j, and here we've got y to the I minus 1. The minus 1 makes it different from this. But with a little bit of manipulation, we can show that this is equivalent to this. Indeed, define h of y equals the sum of I equals 1 to little n of alpha I y of I minus 1. We want to transform this I minus 1 into a j. So we make the substitution j equals I minus 1. Now if I goes from 1 to n, then j is going to go from 0 to little n minus 1. And so I can write this as the sum of j equals 0 to n minus 1. And to make this the same, because j equals to I minus 1, I know that I equals j plus 1. So I get alpha j plus 1, y to the I minus 1 is just j. If you haven't seen this before, it does require a little bit of thought. The claim is that this summation is the same as this summation here. All I have done is change from the letter I to the letter j, and I've shifted it by 1. So rather than I going from 1 to n, my j is going from 0 to n minus 1, but I can recover my I simply by adding 1 to j. If necessary, take a particular example, take little n to be equal to 3, write this out using the dot dot notation, and just show that this and this give us the same result. Now at this point we're essentially done. When I compare this expression here to this expression here, I see that all I have to do is make big N equal to n minus 1. And because little n is a number that is greater than or equal to 1, unless we're dealing about a constant polynomial, and we can worry about that separately and show that all this is true by taking h of y equals to 0. So if we're not discussing a constant polynomial, then my little n will be greater than or equal to 1. And so my big N is going to be an integer that's greater than or equal to 0. And that satisfies the requirement here for a polynomial that my big N is greater than or equal to 0. And then over here, just because I've shifted the index, the fact is that these guys are all just coefficients. And so I can simply define b of j to be alpha j plus 1. And if this is an integer, then this is an integer. And so we see that h of y is indeed of this form here, and so therefore h of y is an arbitrary polynomial. And if p of y has integer coefficients, then h has got integer coefficients. And that proves the claim that for the problem we're discussing, we know that p of y must be of the form h of y times y plus 104,729, where h of y is an arbitrary polynomial, which means that h of y might be 0, or it could be a constant, or it could be some non-trivial polynomial. And because p of y has to have integer coefficients, h of y has got integer coefficients. And any polynomial h of y with integer coefficients will give us a p of y that satisfies the first two requirements.